Okay, set. Great. Well, I hope someone has already said this, but welcome to Dearborn. We're glad you're here. I hope you've enjoyed your time so far and enjoy the rest of it. I hope someone has also had the time to tell you a little bit about the history of the place. I know I don't have the time to do that, but really rather remarkable, the history of both this building and the immediate surrounding area. Obviously, I'm from Ford Motor Company and a longtime HPC user and very much appreciate HPC. I lead a lot of the machine learning efforts at Ford, and so I'm going to tell you a little bit about how we leverage HPC for artificial intelligence and machine learning applications. My first real experience with what I would call true HPC was back in the 90s using NCSA in an Origin 2000 system that was somewhere close to the top of the top 500 list at the time. I looked that up earlier today, and it was rather startling just how small that system now appears in its performance and number of processors and whatnot compared to what we get, what we're fortunate to be able to use every day at Ford. Just very briefly, I'll tell you about some of our infrastructure, what we are using. We have a tremendous amount of data. It's one of the things that is really satisfying as a data scientist in industry is that we have access to so much data. So a big part of our HPC is just about data and data management. We have a very large Hadoop installation, many petabytes, and it's been interesting coupling very large amounts of data with the new compute infrastructure and how we can connect those efficiently and make good use of it, both the data and the compute. We use mostly open source tools for AI model development these days, and it's just been remarkable how fast the industry has moved and advanced, I think largely because of sharing of models and ideas and data and tools. We have, of course, the hardware, and we have just over 500 of the latest generation NVIDIA GPUs is what we use to power most of our AI work right now. We have those on premises, but we can also make use of the cloud infrastructure as appropriate in GCP and Azure and AWS. And then it's really containers that have also enabled a lot of our work, and I'll touch on that towards the end of the talk. I'm going to try to just go through very quickly some examples, some use cases of how we're applying machine learning and artificial intelligence. And part of the motivation for the first one is this is a usage graph of our what we call traditional HPC compute infrastructure that today has over 150,000 cores. I haven't refreshed this graph in a little while, on the slides at least. But you can see that engineers all over the world working for Ford, developing vehicles, are making use of these traditional CPUs. They're running physics-based simulations for the most part. So it's finite element analysis and computational fluid dynamics and the like. And so they're running their physics-based simulations around the clock. Developing a new vehicle still takes years. And a lot of that time taking years is because even though we're doing much of it virtually, these simulations can still take days, weeks, or months. And if we have to do things like virtual crash tests, we run thousands of those. And so again, that takes many months in the development process today, and very useful, but we wish it were a lot faster and a lot shorter. We'd also like to run even more of them. So, as we were discussing briefly at lunch, we've been making use of artificial intelligence or machine learning to learn about those physics-based simulations and be able to recreate them or come very close and approximate them, but in much more efficient, much faster. From a machine learning data scientist perspective, one of our biggest challenges in training machine learning systems is usually coming up with large amounts of accurately labeled data. And so we often do that just by having people label data. or we try to find other clever ways of labeling data. This particular project has been especially nice to work on from a machine learning perspective because, again, we're running all of these physics simulations almost all of the time, and we view this as generating labeled data. So what we're doing in this project is we're training models, in this case deep neural network models, to take the same inputs as these physics simulations and ideally generate the same outputs. But the models are of course not processing all of the physics. They're just trying to learn the output, the results of the physics. Again, every time that we're running a real simulation, we're generating either training or testing data, if not both. So let's see, I'll show you a quick example of that. So for fluid dynamics, or think virtual wind tunnel type of testing, we generated just random shapes. And so those are the ones you see across the top. Yep, right here. We then ran those through the physics simulations and generated steady state fluid dynamics outputs from those. And then we trained a neural network to take inputs like that and produce outputs like that. So we were hoping that it would generalize. And so here's an example in 2 dimensions. So the first column here is the output given these vehicle type shapes and using the Lattice-Boltzmann machine traditional physics solver. Here's the output from running our convolutional neural network that runs 292 times faster. And the error in this case was negligible. So anyway, we're very encouraged by that. Now the speed up that we get when we run in 3 dimensions, because we have not been able to sell a 2-dimensional car, but the speed up in 3 dimensions is not quite 300x, and we're very much pushing the limits of memory and computation when we go to simulating full vehicles, real vehicles that have many millions of points in 3 dimensions. So anyway, we're having a lot of fun with that. Some of the examples, we're already using this in production to design wheels, and we run finite element stress tests basically on wheel designs so that we can optimize the shapes and the materials that we use when manufacturing wheels. We're using it, again, for virtual wind tunnel testing and designing aerodynamics and wind noise and those sorts of things. And as well as things like virtual crash testing. We're very quickly moving to that. Another different example of how we use our GPU infrastructure in HPC is speeding up databases. So in this case, we had 500 million GPS points and growing very rapidly. And with those 500 million GPS points, we wanted to visualize them. And then be able to do traditional database-like things on them, analytics such as joining them, say, with weather data or other road condition data. And so anyway, that was challenging with that many points. But using a GPU-enabled database, I'll show you a quick movie here of zooming in on those, the 500 million points. It works very well. It's essentially real time that we can do both analytics and interactive visualization on these. So I should have had this zoom in on our location here, but this is just down the road. So you get the point. Another application that we're using AI is in machine translation. So you might ask, well, why don't we just use, say, Google Translate? It's a great service, and we're basically emulating it. We're using many of the same techniques since they've been so kind as to open source it. Within Ford, we have our own vocabulary. We have our own nomenclature, and sometimes we call it Ford speak. But certainly for things like we have owner's manuals, we have many more manuals and documents related to manufacturing processes, testing processes, results, all kinds of numerous engineering documents, as well as feedback from the field, so things like warranty claims. And again, we sell, I think last year we sold over 6.5 million vehicles, and about 2 million of those were sold in the United States, but you can imagine that much of the rest were sold around the world. So we run a machine translation service within Ford. It processes over 100,000 translation requests every day. And we've trained it, again, on Ford vocabulary and a lot of Ford documents. And just a few years ago, state-of-the-art in machine translation as measured in the industry standard metric for machine translation is called the BLEU score, BLEU. And state-of-the-art was right around 12 or 13. And just for reference, the very best human translators, so people who do that for a living, are very fluent in multiple languages, score right around 30. Using deep neural networks now, our machine translation is getting to be right around 30. In fact, I just got results this morning for our new Portuguese model that was up in the 40s. So we're very happy with these results. We're deploying them as we speak. And it's been very helpful to be able to more accurately, especially capturing nuances and things that can be very important in translating between different languages. So switch gears again. Another topic that we do is applications of computer vision. Again, really a major change in the capabilities of computer vision occurred in about 2012, 2013 with the introduction of deep neural networks. And so one of the many applications, one of the more fun applications for us in computer vision is working with our racing teams. It's especially fun when they invite us to the races. And our NASCAR team has been doing especially well this year. So anyway, that's been a very fun project. But one of the applications there is that during the race, these vehicles are driving nearly 200 miles an hour. And especially in NASCAR, they bump each other quite a bit. And what we find is, so the teams are allowed to have very high-resolution cameras. So they take pictures of the cars all throughout the race at multiple places around the racetrack. And the teams want to look at those pictures in real time all throughout the race. They're doing things like looking for damage. So if a driver bumps another car, they need to know, is their damage significant enough that they need to go into the pits and have it patched up a little bit, or it's not a problem. They're also looking for debris. So it turns out that on these race cars, nearly everything on this race car is actually a sticker. There's no headlight. There's no grill there. It's all just a picture. It's a sticker. But right here beneath the word fusion is the real grill. And it's very important. If air doesn't flow through there very precisely, the day ends very badly. And here's an example. If a candy wrapper flies onto the racetrack, which actually happens many times in a race, it often gets stuck on that grill. And if it's stuck on the grill for a few minutes and the driver doesn't realize it, the engine explodes. And so again, very bad ending to the day. So people in a semi-trailer at the racetrack, so this is part of the Ford team, they are constantly monitoring these pictures. And they'll tell a driver if they spot a candy wrapper or debris on the grill, and the driver can do something that gets rid of the debris. But they get thousands of pictures every race, and they had the problem that they couldn't find their own cars. So they asked us, could we train a system that would work, again, in real time and detect their cars? So it turns out that detecting the cars is extremely easy. So our system does a great job at that. It's very fast. And then the real challenge is detecting which car is it, because these cars get repainted every race. So one race, the car is sponsored by I don't know, Miller Lite, and the next race it's sponsored by a pizza chain or something. Completely different colors, completely different paint scheme, but their numbers stay the same. So they really wanted to have something. They said, well, just read the numbers on the car. Well, so we started looking at the pictures. Well, what number is this car? Well, it turns out that that's number 78. And so humans really struggled, if they didn't know ahead of time what they were looking for, to read that as number 78. But the computer vision models don't struggle at all. They do a great job with that. So now during every race, we have our system running, and the people in the trailer are looking at their car only because the computer vision is picking out their cars with very high success. But one of the fun things of this project as well was often machine learning models are viewed by end users as black boxes. And they say, oh, there's black magic happening in there. We can't possibly understand how it's working. But we were able to show in this case that when we interrogated the model, and we gave it this picture on the right, and we asked it, in this case, we looked at the activations. So again, this has been trained to try to read the numbers. We did that by giving it many, many examples. That's all we did. We didn't tell it where the numbers were or even what numbers were. We just gave it many examples. And then when we looked at, well, what is it looking at in this picture? And where white is more important, it turns out it's reading the numbers. So we were able to show them that it's not entirely a black box. We can take the covers off, and you can understand how it's working a bit. And so that was also very nice. And as I said, we've deployed this. It's running at all of our races. And so it was a very nice example where we could train something in HPC. It can run in production. And I'll talk about containers a little bit at the end, but that also helped in this process. Another application of computer vision, a little less fast, is in the manufacturing plant. We produce vehicles typically at a rate of about 1 a minute in a plant. So they're moving fairly slowly down the line. But we've put cameras all over our plants in the last couple of years because we found that with computer vision we can do excellent inspection. And so one of the challenges in inspection, in this particular example, is that there are many different wheels that are available for most vehicles. And most of them are interchangeable. So it's possible, highly unlikely, but possible that one set of wheels could go on one side of the car and a different set of wheels could go on the other side of the car. And it turns out that that's a very difficult thing for inspectors to see because unless you had mirrors set up, you don't see both sides of the car at the same time. And many of our wheels are very, very similar. So to be able to look at a car on one side and then walk around to the other side and remember which ones you should be seeing is a little challenging. But it turns out that's very easy, again, for computer vision. And one of the things that I liked in this example was just how robust this computer vision system is, that it can work even when it's not seeing the whole wheel. It can be seeing actually very little of the wheel and still get it right. So I don't know how clear this is on the projector, but this is one style of wheel. And of course, when it sees the whole thing, it's very easy for it to get it. When it sees even part of it, this is a different wheel, but somewhat similar shape, at least if you just saw part of the wheel. It can still see it. In this case, it was only seeing this little sliver of the wheel, and it got it perfectly right. It knows exactly what wheel that is, even when it just saw that little sliver. I couldn't even figure it out. And same thing over here. It just saw a little part of the wheel, and it knew exactly which of these wheels or which type of wheel it was. So one of the many applications that we've deployed in computer vision and manufacturing. Another one is inspecting paint. So it turns out that if you have a speck of dust in the paint shop, our paint shops are becoming not quite as clean as, say, a computer chip fab facility, but still fairly clean because one speck of dust makes a very tiny imperfection in the paint. And it's something that, of course, we want the cars to be perfect. So we've put in place computer vision systems that can find those defects, and then it turns out it's very easy to fix them if you find them either before you bake it or at just the right spot in the manufacturing process. Let's see. Oh, another example of computer vision is in labeling data. So as we could talk all day about autonomous vehicles and the journey that everyone is on towards autonomous vehicles. But one of the things that we're working on that path is semi-autonomous vehicles. And an important part of semi-autonomous vehicles is driver monitoring. And as part of that, we have in our developing even more advanced systems to detect, say, is the driver paying attention? Does the driver have hands on the wheel? So things like gaze detection are very important. But in this particular example, the engineers had many hours, tens of thousands of hours of video of drivers using systems that they thought could detect if hands were on the wheel or not, how many hands, but they needed to check it. And they started labeling it by hand and found that that was very difficult. So we were able to move to the data center and very quickly developed systems that could check those automatically and very accurately determine is it seeing that there's one hand on the wheel or two or not at all. So anyway, it was very useful even for providing just more labeled data for other systems. One of the things that we're using AI for is to automate the data scientist's job, or at least parts of it. So we're using AI to build more AI. One of the big time-consuming parts of a data scientist's job is tuning hyperparameters in the models. So I think of it as the knobs and dials of machine learning and building machine learning models. And this used to take us a lot of time and could chew up a lot of compute resources as well. Now we just chew up even more compute resources. So we've traded off, although we're still hiring data scientists, we at least need to hire fewer additional data scientists because we're using more compute hardware. So where one data scientist previously might have been using, say, 4 GPUs as they're developing a model, now they're using 40 or 80 or 120 at the same time because they're using this type of technique to automate their search for optimizing hyperparameters. So I mentioned containers. So one of our big struggles a few years back was that our HPC environment at Ford was extremely efficiently run and very secure. But sometimes we needed to run, I'll call it cutting-edge software. And that software might be released, say, for a different flavor of Linux. Or we might need a different GPU driver to run certain software than to run different software. And so that was not compatible, right, with running a very large HPC installation that was being used by thousands, if not tens of thousands of engineers around the world. So that was completely solved when we moved everything to containers. It also enabled us to move from desktop and desk-side systems. So I can develop something, or a data scientist can develop something on a high-end laptop, and then very easily and seamlessly move that to our data center, to our HPC compute environment. And there's no work to do that anymore. It's all just done with our containers. But when we started using containers, we were then struggling with container management. So we were programming the communications in MPI, and we were programming for resiliency, and we were not enjoying doing that. And then Kubernetes came along. And Kubernetes has made many aspects of our lives much nicer and much easier as we now use that to manage containers and even to deploy many of these models that I've shown into production through containers. So just to summarize, this is actually a picture of our new data center that just opened this past June. It is in the shadow of Ford World Headquarters, probably about 1.25 miles from here. And These actually are the racks that contain our GPU servers. And again, I've talked about some of the applications like natural language processing, computer-aided engineering and computer vision. I didn't talk about some of the other applications that we're using them, such as in Ford Credit, in credit decisioning, and legal applications, along with many others. And the big enablers for this just explosion in capabilities and what we've been able to do using AI and machine learning has been the data, the availability, and just the ability to manage and curate so much data, the availability of open models and software and algorithms, and then advances in hardware such as GPUs and the really fast networking between our storage and our compute. And then, of course, containers at least has made our lives easier. So I think I'm just about out of time, and I don't know if you're taking questions. Okay, happy to take questions.
Where do you see the use of HPC versus big data in your analysis? So you've got the machines, obviously. What makes it an HPC problem for you in terms of timeliness, in terms of size, in terms of I/O that you can't just hand off to a large compute facility like an AWS or whatever?
I'm not sure I totally understand your question, because, and it may have to do with how we're set up at Ford. So at Ford, our big data infrastructure is under the umbrella of our HPC infrastructure. So it's all integrated, and it's run by the same team, which has been terrific. Because they're such a terrific team, and two, because they can make sure that everything works very well together. If your question is about how do we decide whether to run it in our own HPC infrastructure versus, say, AWS or something?
Well, no, it was, when do you go to HPC for the problem, or when do you go with your other compute? And what are the heuristics that say go to the HPC solution?
Sure. Okay, so if the question is, what would lead us to HPC versus traditional compute? So these days, training AI systems almost entirely we're doing in HPC, because they are they're either so compute intense or they're using so much data. And again, our big data is within our HPC ecosystem. Excuse me. So if it either is using petabytes of data or it's using a lot of compute, we're going to HPC. And most of training machine learning these days is doing that. For deployment, that's where then we're moving to our traditional computer environment. So, but again, containers and Kubernetes are making that even easier, because both are now running that. So a lot of, again, developing these models, training them, we're doing in HPC, deploying them and running them in production is going to traditional compute.
If I could ask you, relative to the whole HPC environment, in just very rough terms, what % is doing artificial intelligence, machine learning, or deep learning? Just if you looked at the whole hardware, is it like 25%, 50%, or whatever?
I'm probably not the best person to answer that. And it's hard to tell because it's largely different parts of it. So within our HPC, I can, at least within my own mind, I can divide it up into, we have the traditional compute, which is mainly CPU-based. We have our big data infrastructure, which is Hadoop-based. And a lot of that is running Spark. And so some of the machine learning we're running there. Spark ML is great. And then we have now this sort of third part, which is the AI GPU part, and that's not 100% AI ML, but 90-some%. And so there's probably 5% of the traditional CPU compute that's running machine learning. There's probably 60%, or if not higher, of the Hadoop part, that's the compute part of that, that's running machine learning. And then it's 97% or 8% in the GPU part.
Great, thank you.
Yes.
Hi. Hi, Brian. I think the idea of your labeling simulation results to create useful data for further machine learning is actually quite fascinating. Many people have complained about manufacturers running CAE or other kinds of simulations and then not keeping the information or not doing much with it. So I'd be curious to know what's your infrastructure for that, because typically simulation results are quite large.
Yeah.
So how are you managing? Do you have a research data management or a data storage capability, object storage? What does that look like? And how long ago did you start doing it? And maybe get some, if you're prepared to share, how big is it now?
Sure. Yeah, I think I would say we started saving as much as we could a little over a year ago, not quite a year and a half ago, when we realized the potential of this. You're absolutely right. It was a big mind shift for our engineers who were used to, boy, that's big, throw it out. Even just keeping the results. We often don't care about anything in the middle. It's just what went in, what came out. And it was even a big change for a company like Ford, just anyone in the auto industry. It's unfortunately, right, we're all aware of how many, say, accidents and injuries happen every year related to transportation. That results in being a very litigious industry, or a litigious target industry. And so that has even shaped, call it the data strategy of automotive OEMs over the years. So that took some workings to get some of those both policies and mindsets changed. But I think we did that. Storage is expensive, but relatively cheap compared to many other options and many other things. So one of the things that we did was we put in place tens of petabytes of storage additional, both Hadoop and GPFS. Sure. And we've been filling it up. And so then, of course, the challenge is prioritizing what to save and what not. But that's where we're at. Yes.
Hey there, that was unbelievable. Algorithms and the kinds of math you're using, are you innovating yourselves algorithmically? Are you using standard algorithms? Do you have internal algorithmists and data scientists who are leading the charge? Are you leveraging services through the cloud service providers? Just where's the innovation coming from in the skill base?
Sure. Well, our first choice is to use whatever's available. So we're very happy if we can use, say, publicly available algorithms, be it models, frameworks. So tools like TensorFlow and PyTorch are terrific, and we make great use of them. So for something like computer vision, if you want to detect objects these days, the standards are quite good. If you're trying to develop something to detect objects, say for a vehicle application, then we work on certainly fine-tuning those and improving them to the best that we can, rather than just accepting whatever we can get off the shelf. But for the most part, those types of problems are fairly easily solved now with openly available algorithms and tools. But for some of the problems, like say, especially when we get into the three-dimensional space, there's not much available. And so we're having to do an awful lot of development. So again, generally we would prefer not to. I'd rather if it was available either to buy or just use. But it's just, we haven't found that it is. So we have a fairly large team, or in teams, developing algorithms. We have a lot of mathematicians. And at least I think the positive is they get to work on really challenging math problems. And so there's been no shortage of that. So a lot of it we're having to develop ourselves, especially in the 3D space.
And just on that point, are there certain kinds, thanks, are there certain kinds of methodologies that look more promising to you on that? I mean, like, reinforcement learning or GANs. I mean, are there certain things, or are they very specific to the problem set that you're attacking,
No, I think I would say just generally an answer to that is we're finding that the more general an algorithm is, the more useful it is, and even the better it's performing. So sometimes we end up with a fairly specific method to solve one problem, but usually that gets replaced fairly quickly with something that's more general. And just about anything that we develop for one problem we're finding is very applicable to many other problems.
Okay, are there any other questions? Okay, Bryan, thank you very much.